what we have done in the last class? Anyone? Can anybody tell me what are the things we have discussed in the last class? What you mean by depletion region? What you mean by extrinsic semiconductor, intrinsic semiconductor? What you mean by depletion region? What you mean by no bias state? What you mean by valency band? What you mean by conduction band? Can anybody tell me those just brief about? Anyone? Yes. Anyone? Yes, Nivedita is here. Nivedita?
Yes, sir.
Yes. Can you just tell me, Nivedita, what are the things you have heard in the yesterday's class? What are the concepts you have heard? What you have understood from the yesterday's class?
Like P-type and N-type semiconductors.
Okay.
Definition for conductors, semiconductors, insulators,
Okay.
and semiconductor types, intrinsic and extrinsic,
Okay.
and
Hmm.
types of diodes.
Types of diodes. Uh, okay. Uh, and then, can anybody tell me what you mean by PN diode? What do you mean by PN junction diode? Is anyone? What do you mean by a diode? Yes, Naveshri is here. Yes, Naveshri. Yes, Kevin D'Souza is here. Kevin, are you there? Kevin, are you there? Is Nitish Kiran? Nitish Kiran? Nitish? See, unless and until you reply me, if you do not active in the class, so if it is, there is no necessary for you people to take the class. Nitin MS is here. Nitin MS. Nitin MS. Yes, Nitin. What are the things you have learned in the yesterday's class? Can you just tell me what are the terms you have heard in the yesterday's class?
Excuse me, sir.
Yes, Nitin.
Yes, sir. That all PN junction diodes,
Yes.
this one P-type, N-type, and all, sir.
Yes. What do you mean by in P type? What are the majority charge carriers, Nitin?
Sir, in P-type holes, sir.
Yes, very good. In whereas in the case of N type,
Electrons, sir.
okay. What do you mean by depletion region?
Depletion region, it is the region formed in between the P and this one, sir.
Hmm.
Charges
Hmm.
accumulating in between the diodes, sir.
Okay. Hmm. Okay, good. Nitin. Okay, very good. Okay. Next, Manasa is here. Manasa V. Manasa is here. See, those who not respond, I will simply remove from the meeting. Okay. So from today onwards, I will do that. Is it clear? Yes, Meghana is here. Meghana BR. Meghana.
Yes, sir.
Yes, Meghana. What are the things you have heard from the yesterday's class? What you know from the yesterday's class? What do you mean by PN diode? PN junction diode? Hmm. What do you mean by PN junction diode? Manasa? Meghana BR. Hmm. Yes, Akram is here. Muhammad Akram is here. Rahul is here. Rahul.
Sir,
Yes, Rahul. What are the things you have heard, Rahul, yesterday's class?
intrinsic semiconductor, extrinsic semiconductor.
Yes, Rahul. What is the difference between them? Can you just name one or two differences?
Intrinsic semiconductor is a pure semiconductor, sir.
Very good.
And extrinsic is a some impurities adding
Okay.
dopings.
Yes. What are the two types of impurities we have, Rahul?
Silicon, germanium.
No, those are the semiconductor type. Okay. So impurities. So what are the types of impurities we have? So one is a pentavalent and one more is a trivalent, right?
Trivalent. Yes.
Yes. If we add pentavalent, the silicon material will become.
P-type.
If we add a pentavalent, if you silicon material will become which type of material will become?
N-type.
Okay. If we add a means a trivalent element, what is the element? It will become silicon.
P-type.
Yes. Okay. 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 So I think okay, you heard you know some of the basic concepts what we have learned. Okay. So today we are going to see the more details of that in the today's class. Okay. So let me share the PPT. So whether the PPT is visible now, can anybody confirm me?
Yes, sir, it's visible.
Okay.
Sir.
Okay. Thank you. Okay. So today what we are going to do is the same thing what we have learned in the yesterday's class. So the continuation of the things we will be going through it. Okay. So you can see here, I will be taking a single layer. On the single layer, I will be having a doping concentration. I will do it. On the left side of the layer, what I am going to do is I am going to add a trivalent impurity so that the material, silicon material will behave like a p-type material, whereas over here I will be adding a pentavalent impurities for the right side of the that is the layer, that is a silicon wafer what I have taken, so that the majority charge carriers will be free electron. So now you can see here, because of the concentration level, so because at the left side you have a holes, high amount of concentration of holes you have, and the right side you have a high amount of free electrons you have. So what happens is, because of the difference in concentrations, the holes try to move from the p-type material to n-type material. Similarly, the electrons which are there in the n-type material, they will try to move from n-type material to the p-type material. So what happens is, so they will come near the junction, and that junction we call it as a depletion junction, or it is also called as a diffusion. So what do you mean by diffusion? So diffusion is nothing but, so some of the free electrons which are there in the n-type material, they try to attract it by the holes which are there in the p-type material, and they will come up or they will diffuse into this p junction, and that process we call it as a diffusion mechanism or a diffusion process. Similarly, in the case of holes, what happens is, so because of the high concentration, so generally what happens is, so the flow of anything will goes from high concentration to low concentrations. So therefore what happens is, the holes will try to attract it by the free electrons. So they will absorb some electrons and they will become a immobile ion near the junction. So that junction we call it as a depletion region. And you can see here, the negatively charged ions are there in the p-type region, and the positively charged ions, that is the immobile ions, will be there in the n-type material. So the region corresponding of this negative ions and the positive immobile ions, so we call it as a depletion region. So it is something like a wall. It has been established between your p-type material and a n-type material. So now what you are supposed to do is, if a current has to pass through this diode means, then we should give some external circuit, or we should give some external voltage or a current through it. So how we are going to give a current or a voltage to that? So that depends upon the biasing methods. So you can see here, the depletion region. It is also called as a depletion region, and also it is called as a space charge region. So in this space charge region, there will be no mobility of the electrons will takes place. So it depends upon the width of this depletion region, depends upon what is the type of material we have taken and how much level of dopant we have added to this silicon wafer, so that it become a p-type material and n-type material. So depending upon those factors, so the width of this depletion region will be decided. Okay, so as I told you, so because of this immobile ions, so the negative charge ions are there, here positive charge ions are there. So therefore what happens is there is a voltage difference will be existing in this barrier potential or in the depletion region. Okay, and similarly in the n-type material, so because of the positive ions which are deposited at the across the junction, so there will be a positive voltage or the positive voltage difference will be created in this junction, and this negative junction and this positive junction threshold voltage. Okay, just a bit a minute. That junction barrier voltage, we call it as a threshold voltage. Okay, so we call it as a threshold voltage. You can see here the p type, there is some potential means there is a voltage difference is there, and here also the voltage difference is there. So therefore there is an voltage difference is has been exerted in the depletion region. So in order to overcome this voltage, so we need to provide an external voltage which is greater than this voltage. Okay, so this junction barrier voltage, it is also called as a threshold voltage, or it is also called as a cut-in voltage. Okay, so and how we operate this junction or how we operate this PN junction, depending upon that we have a three types of biasing methods are there. So the first one we call it as a no bias condition, and the second one we call it as a forward bias condition, and the third one we call it as a reverse bias condition. So what do you mean by biasing? Biasing, it is nothing but it is a process of applying some external voltage for the diode. It is a process of applying some external voltage to the diode. We call it as a biasing. So there are three types of biasing methods are there. The first we call it as a no bias condition. The second we call it as a forward bias condition. And the third one we call it as a under reversed bias condition or a reverse bias condition. Okay, so the first one we call it as a no bias condition. The first one we call it as a no bias condition. So what you mean by no bias condition is, so if I do not apply any voltages, if I do not apply any voltages across the terminals of the PN junction means, then that form of process of giving the input for the diode, we call it as a no bias condition. So in the no bias condition, there will be no current flows across the diode. Okay, so that we call it as a no bias. So even though if you connected the battery charge will be zero. Even though if you connect the battery or even though if you give a voltage supply, so the voltage supply which you're applying to this P type and N type, it should be zero. So that condition we call it as a no bias condition. So if that is the case means, so if I try to want to see what is the voltage is there between this P type and N type. So if I take an voltmeter and if I measure the voltage between these two terminal means, then I will be getting some voltage across the voltmeter. We will be using a voltmeter. So in order to measure the voltage between the two terminal, so under no bias condition, so means what? If I do not apply any external voltage to it, so if I want to measure what is the voltage is there across these two terminals, if I do means, then there will be some voltage will be there. So what is that voltage? So it will be 0.7 voltage for the silicon material, and if you are using the germanium semiconductor means, then the voltage between those two elements or the voltage between those two P and N junction will exert a 0.3 voltage. So this voltage we call it as a potential barrier voltage, or also it is called as a junction barrier voltage, or it is also called as a threshold voltage, or it is also called as a cut-in knee voltage. Okay, so these are the different names what we have created for this junction barrier voltage. So under no bias condition, there will be no current flows across the PN junction. Is that clear to everyone? What do you mean by no bias condition? Yes? No? Yes, Naveen?
Yes, sir.
Okay, so it is very simple. When so if I take an PN diode, so that state itself we call it as a no bias state because we are not applying any external voltage, so we call it as a no bias process or a condition. Under this, if I measure an voltmeter across to this terminal means, then I will be getting a 0.7 voltage in the voltmeter. If it is a if it is a silicon material, if it is a germanium material means, then you'll be getting a 0.3 voltage. So the next one we call it as a forward bias PN junction. What do you mean by forward bias PN junction is, so you can see here, if the positive terminal, if the external battery what we are connecting for this diode, if the positive of the battery, if it is connected to the p-type material or the p-type element, and the negative element or the negative of the battery, if it is connected to the n-type element means, then such a configuration we call it as a forward bias PN junction diode. So such a combination we call it as a forward biased PN junction diode. So under this condition, what happens is the current will flows across the PN junction. So when the current will flow, when the input voltage, if it is the input voltage greater than the junction voltage or the barrier voltage. So what I told in the previous slide, I told you, right? So the barrier voltage is 0.7 for the silicon and 0.3 for the germanium. So if the input voltage what you are applying across the battery, if the input voltage is greater than 0.3 voltage means, then the current will start moving from p-type material to n-type material. So in the conventional, you can see the diagram how we are writing. So the current will move from positive terminal of the battery. The direction of the current will flow from positive terminal of the battery, and it will end up in a negative terminal of the battery. So under this condition, so the current which is flowing across the diode, it will be having a maximum current. So IF is nothing but the current which is passing across the diode. So we call it as a forward current. IF is nothing but forward current. So IF will be having a maximum current. Is that clear? What do you mean by forward bias diode? Yes?
Yes, sir.
Okay,
Yes,
forward
sir.
bias. Okay, simple. Positive terminal you can connect to positive, and negative terminal you need to connect to negative. Why there will be current flows across is because, so you can see here, since you are connecting positive to p hole, so means what, the same elements will repel each other. So therefore what happens is these p holes will try to move from this junction. Similarly, the electrons we have connected to the negative battery of the negative terminal of the battery. So they will start to repel. So means what, they want to cross this junction. So because of this high amount of force which has been exerted both from the p-type material and the n-type material, so whatever the barrier is there, so that barrier will be broken down when the input voltage is greater than the junction voltage. So the moment when the input voltage is greater than the junction voltage is there, so the current will start flows across from p-type material to n-type material. Okay, actually electrons will move in the for the flow of electrons, but for the conventional what we say that, so the electron will be or the current will move from p-type material to n-type material. Okay, so this is we call it a forward bias PN junction. Okay, and you can see the diode symbol how we are writing. So for the anode we will call it as a positive terminal, and for the cathode we call it as a negative terminal. So this is how we are going to represent. P plus means it is a p-type material, minus means it is a n-type material. Okay, so this condition we call it as a forward bias condition. So the next one is reverse bias PN junction. So what do you mean by reverse bias condition? So in reverse bias condition, so whatever the terminals we have applied in the previous case, no, we will reverse it. We will reverse it. So what do you mean by that? You can see in the diagram, the negative terminal of the battery, it is being connected to the positive terminal of the diode, that is p-type material we have connected. Similarly, so the positive terminal of the battery, it is connected to the negative n-type element. So in such a case, what happens is, so the majority charge carriers will start to attract for this negative terminal of the battery. Similarly, the majority charge carriers, that is the electrons in the N type, they will try to attract this positive plates, which has the positive voltage what you are applying from the battery. And one more thing what happens is, so the minority charge carriers are there in the P type, no? So they will start to repel and they will try to accumulate in this depletion region. And similarly, the minority charge carriers which are there in the N type, that is holes, so they will start to repel it because we are applying a positive voltage. So the minority charge carriers, they will be having a repel voltage will be exerted. So because of that, they will start to move in the opposite direction. So you can see the P type, it is moving in the opposite direction, means outward direction. Similarly, the N type are moving in the outward direction. Why? Because you are given a negative voltage for the P, that is holes, and for the positive voltage you are applied for the negative electrons. So therefore they will start to attract each other, whereas the minority charge carriers, they will repel each other and they will come and situate in the depletion region. So because of this, what happens is, so the current will not flow, means the continuous path or closed path will not be established in the diode, and such a combination or such a configuration we call it as a reverse bias condition. So under reverse bias condition, the current which is flowing across the diode, it will be zero. So there will be no current flows across the diode when the diode is operated in this manner. So what is this manner? Reverse bias manner. So you can see here what we have done is we have reversed the diode. So initially in the previous case, you can see the diode was positive was given to positive and the negative was given to the negative. But in this case, you can see here the positive terminal of the VR, it is connected to the negative, and the positive terminal of this, it is being connected to the negative with the use of this R resistors. Okay, so therefore under reverse bias condition, there will be no current flows across the diagram. So you can see here the switch is open. Open means what? Here the circuit will not be closed. So therefore the current will not flow across this circuit. So therefore, in order to ensure the diode is not working, so we will be representing in this manner. You can see the after the symbol there is a circuit diagram is there, right? So you can see the switch is open. So switch is open means there will be no current flows across the diode. So there will be minimum current, that is a minimum current we will be following, but we will discuss that in a later. But under reverse bias condition, the PN junction will not work, or the current flow through the majority charge carriers is not possible. Okay, so this we call it as a reverse bias PN junction. Is that clear? This one, reverse bias. Is it clear? Okay.
Yes.
Okay. Okay. So you have understood three biasing mechanism: no biasing, forward biasing, reverse biasing. Okay. No biasing means no external entity voltage you are applying. Forward bias means positive terminal to positive, negative terminal to negative. So current will flow across the diode. So it is called as a forward bias condition. Reverse bias condition means positive terminal you are applying to negative of the battery, negative of the N type you are connecting to the positive of the battery. So in reverse bias junction, there will be no current flows and the depletion region will also width. Why? Because of the minority charge carriers, the width of the depletion will go on increases. So means what is putting like a something like wall in between the two entities. So if they want to try also, it is not possible for us to break up the wall. Why? Because the width of the wall is very large. So therefore, the current will not flow across in the reverse bias PN junction. Okay. So the next one, it is a characteristics of the PN junction. So they will ask you the characteristics of the PN junction. This is very, very important concept. Okay. So what you mean by characteristics of the PN junction is that, so the variation of input voltage with respect to the output current, the variation of the input voltage with respect to the output voltage, we call it as a characteristics of the PN junction. So these characteristics of the PN junction, we need to analysis for all the three biasing condition. When no bias, when forward bias, and when reverse bias happens, no. So under this condition, we need to check what is a VI characteristics. It is also called as a VI characteristics of the PN junction. Why it is called as a VI characteristics? Because voltage you are applying for the diode and current which is flowing across the diode, no, you are monitoring in function with the voltage. So therefore it is also called as a VI characteristics of the PN junction diode. So now you can see this graph carefully. So you can see the x-axis, it is having what it is having, forward bias voltage. So forward voltage, VF means forward voltage. So that is the input what you are applying from the battery. Now you can see here, and the vertical axis. So what is the vertical axis? It is a current, or we call it as a forward current. So the current which is flowing across this circuit, we call it as a forward current, or the current which is flowing across the diode, we call it as a forward current. So now you can see here, the current has been represented in terms of milliamps. So because we have taken a low power device diodes, so therefore the current which is flowing across the diode, it will be in terms of milliamps only generally. Okay, so now what we are trying to do is we are trying to find a relationship between the input voltage with respect to the output current. We are trying to find a input voltage. Why I am calling it as a input voltage? Because the input supply what we are giving from the voltage source, so therefore I am calling it as a input voltage. So because of this application of input voltage, you are getting some current from the diode. So therefore we call it as a output current. So therefore it is called as a VI characteristics of the diode. So now you can see here, when the input voltage is 0, so means what? It is a no bias condition. So when the input voltage is 0, you can see there is no current which is flowing. So there is no current which is flowing. So means what? Under no bias condition, so there is no current which will be flowing across the diode. So therefore, when input is equal to 0, your voltage is also 0 and your current is also 0. Now you see what I am trying to do is I am gradually increasing the voltage. I am gradually increasing the voltage. How? From 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, I am increasing like this. So if I gradually increase this, what is happening is, so current is also increasing gradually. It is in the, let's say it is less than 5 milliamps. Okay. And I told you, so what I told you, so when the input voltage is greater, less than the means threshold voltage or a new voltage, there will be no current flows across the diode, I said. But in the graph, you can see a minimum amount of current is flowing. Why it is? Because this is because of the minority charge carriers which are there in the diode. So the minority charge carriers which are there in the diode, no, so they will be having a movement from positive to negative. So because of the minority charge carriers, slight current will be flowing across the diode, and that current in practical it is negligible. But for the VI characteristics, we will be mentioning that in terms of some milliamps, less than 1 milliamps or less than 2 milliamps only. Okay, so now you can see here, as the input voltage reaches the knee voltage, so you can see at 0.7, so we have given it as a knee voltage, that is called as a barrier voltage or a threshold voltage. So you can see as the input voltage reaches the knee voltage, suddenly there is an increase in current. Why? Because the diode start flowing the current, or the diode starts permitting flow of current. So therefore the current across the diode will start increases if you increase a small amount of voltage. So therefore what I can do, give a conclusion from this is, so when the input voltage is less than the forward voltage or less than the knee voltage, a minimum amount of current will flow across the PN junction because of the minority charge carriers. As the input voltage is greater than the threshold voltage, there is a drastic increase or linear increase in the current which takes place across the diode. Okay, and it will be in the order of, you can see here, for the input voltage, let's say for the input voltage is at 0.8, so you can see what is the current, it is around 60 amps. So for the input voltage, if you just increases the 0.1, so you can see from 0.8 to you have went to 0.9, so the current what it is taking, approximately it is taking 100 milliamps. So means what, whatever the input you are applying, for that corresponding output what the current is getting, so that current will be flowing across the diode. And now you need to see about what is a knee voltage. So the knee voltage for the silicon, I told you 0.7 volts, that is a cutoff voltage, and for the germanium it is 0.3 volts. Okay, so if the input voltage is greater than 0.7 volts for the silicon diode, means then the diode will start conducting and you will be getting the waveforms like this. Similarly, if the input voltage, if you have taken a germanium means, then the input voltage is greater than 0.3 voltage means, then the diode will start conducting in this manner. Did you understood this one? What do you mean by PN characteristics? PN junction characteristics? Yes. Shall we go next? Yes,
Yes.
no.
Yes, sir.
Okay. So you can see here, so in order to see what is the current which is flowing across the diode, so we will be using this equation. So what is that? So the diode forward current will be represented, mathematically represented by using this equation. So what is that? IF is equal to I naught into e power V divided by eta Vt minus 1. So I request everyone, please make a note of these equations. So the forward voltage, so the forward voltage, you can see if the voltage V is greater than the cut-in voltage, then the barrier potential will reduces and IF will increases linearly. So how they are dependent? So in order to see the dependency of the barrier voltage along with the forward current of the diode, so we have one expression. So what is that? IF is a forward current of the diode. So it is a forward bias of the diode. So I naught into e power V divided by eta Vt minus 1. So where IF is a forward diode, I naught is a reverse saturation current. I naught we call it as a reverse saturation current. When you apply a voltage of V, and Vt is the thermal voltage. Vt is the thermal voltage of the diode. So we are going to calculate the thermal voltage of the diode by using this equation. So what is that? K into T divided by Q. K into T divided by Q, where T is, we call it as a Boltzmann constant. The value of the Boltzmann constant is 1.38 into 10 power minus 3 joules per Kelvin. And T is nothing but the temperature, absolute temperature, and we will be taking it as a 0 degree Celsius. It is not a 0 degree Kelvin, we will be taking it as 0 degree Celsius. And Q is nothing but a charge of the electron. Q is nothing but a charge of the electron, and it will be given as 1.6 into 10 power minus 19 coulomb. So means what? One charge. So one charge is nothing but 1.6 into 10 power minus 19 coulomb values will be there. And eta we have used, that is n. It is something like it is representing n line. So it is nothing but it is a constant which depends upon the physical construction of the diode what we are using. So for silicon it will be 2, and for germanium the eta it will be 1. Okay. So these are the equations what we will be using in order to find out the forward current of the diode. Okay. So where I naught is nothing but the reverse saturation current, Vt is nothing but the thermal voltage. See, the thermal voltage is of the diode. It will be fixed. Okay. And it depends upon the temperature of the room. Okay. So it is nothing but Kt divided by Q. So we are going to represent Q divided by Kt. Why? Because I will tell you in the next one, because we have 1 plus Vt is there. So therefore we have written Q by T. So you'll be getting 11600 you'll be getting, and that we will be using it in the problem solving mechanisms. Okay. Did you understood this one? Yes? No?
Yes, sir.
Okay. So now you can see here. So we want to measure what is this Vt, that is a thermal voltage of the diode. I told you, right? So what is this Vt I want to measure? So in order to measure this thermal voltage, so these are the calculations what we have given. So the thermal voltage of the diode we have given it as K into T divided by Q. So I told you K is nothing but the Boltzmann constant. The value is 1.38 into 10 power minus 23 joules per Kelvin. And temperature is nothing but in degree Kelvin we need to mention. Okay. So it is nothing but 273 plus the temperature of the room temperature. So generally what we call it as room temperature is 27 degrees Celsius. We will be taking as a room temperature. So therefore what happens is your temperature, that is T, is nothing but 273 plus 27, it is nothing but 300 you will be getting. Okay, so generally the room temperature we will be taking it as a 27 degrees Celsius. The next one is Q. So Q is what? The magnitude of the one electron charge. So the magnitude of the one electron charge, it is nothing but 1.6 into 10 power minus 19 coulomb. So if I substitute all these expression in this Vt, that is nothing but Kt divided by Q. then what you'll be getting is, so you'll be getting Vt is equal to 0.026 volts you'll be getting. So if I represent that in terms of millivolts means, then you'll be getting Vt is nothing but 26 millivolts you'll be getting. Okay, at a room temperature. So the thermal voltage of the diode. So the thermal voltage of the diode, we will be having a 26 millivolts for the silicon. Okay, I request everyone, please make a note of this. Yes. So once it is over, you please tell me, we will go to the next section. Is it over? Shall we go next? No? Yes? Yes, Kavya, shall we go for the next?
Yes, sir.
Okay. Okay. So the next one is, we need to talk about what you mean by reverse characteristics. Meaning that forward characteristics of the PN junction we saw. Okay, so when I give a positive voltage for the diode, so what happens to the PN junction, I understood. So if I apply a negative voltage for the diode, what will happen? We need to understand. Okay, so that we call it as a reverse characteristics of the PN junction. So you can see in the diagram. So for the diode, so for the negative terminal, we are applying a positive voltage, and for the positive terminal of the diode, we are applying a negative terminal. So this configuration, we call it as a reverse bias condition. So now you can see here, when the input means when the voltage, see, since we are applying a negative voltage, so you can see here the input voltage is negative. So you can see here minus VR is there. Reverse bias is minus VR is there, and you'll be getting a negative current. You will be getting a negative current. So therefore you can see here minus IR is there. IR is the reverse current. Since you are getting a negative current, means whatever the direction you got in the previous case, no, so the opposite direction you are getting. So therefore we will be representing in terms of minus IR. So now you can see here what happens is, so when the input voltage goes on increasing in the negative direction, the current is also very, very minimum in the reverse characteristics of the PN junction. So you can see here it is less than 10 nano amps. So you can see when the input voltage is increased to minus 80 volts, so there also you are getting the output of the PN junction diode, you are getting less than 10 nano amps. So why? Because the reverse bias condition, the diode will not be means it will be off state. So therefore the current will not flow across the diode. But as and when you increase the reverse voltage, means the voltage what you are applying for the terminal, if you increase certain beyond the value, means then the reverse breakdown will happen. At that instant of time, your diode will start flowing in a linear manner. So you can see here, when the input voltage is still negative, when you compare to minus 80 volts, so that we call it as a minus VZ, then there is an increase in reverse current which is flowing across this. So this condition we call it as a breakdown region or a reverse breakdown region. Okay, so under reverse breakdown region, what happens is the diode will start conducting, but the diode will be breakdown. So means what? We are applying a very high amount of negative voltage across that. So therefore, your diode will be breakdown, and the current will start flowing linearly in this region. Okay, so this is a reverse characteristics what you will be getting from the PN junction. Okay, so you please make a note of this. Please make a note of this diagram and the circuit diagram. Shall we go for the next? Shall we go for the next? Yes? No? Yes, Arpita, shall we go next? Yes, Manish?
Yes, sir.
Okay. Okay. So this is the one thing. So if I see that, if I combine both forward characteristics and reverse characteristics, we call it as the complete VI characteristics of the silicon or a germanium diode. So it will be same for both the silicon and germanium. It will be same. Only the cut-in voltage will change. So for the cut-in voltage for the silicon, it will be 0.7 volts, and for the germanium, it will be sorry, it will be 0.3 volts. So you can see here when the input voltage in the forward direction, you can see this one. When the input voltage is when the diode is in forward bias condition, so the input voltage as it increases, so when the input voltage is greater than the threshold voltage, so the current will starts flowing. So this we call it as a forward current. In the reverse condition, you can see here, if the input voltage is too much negative, so then the diode breakdown will happen. Why? Because there is a large number of depletion regions will be created, and because of this high reverse voltage, the breakdown will takes place. So there are two types of breakdowns are there. One is avalanche breakdown. I think you have already studied this in a second PUC configurations. Okay. So we will see that explanation details. So why reverse breakdown will happen in the diode. But for the time being, you should see that when the input voltage is applied negatively very high, in the case of reverse direction means, then the breakdown of the diode will takes place. So when the breakdown of the diode will takes place, high amount of current will be flowing across the diode. So this entire diagram we call it as a VI characteristics. So in the VI characteristics, you should mention this diagram and what are the scenarios which will happen in the positive direction and what are the scenarios which will happen in the negative direction. You need to explain. Okay. Did you understood this one?
Yes, sir.
Okay, so they will ask you one simple question. They will ask you for 8 to 10 marks. Definitely one question will be appearing from this. So what they will be asking you, explain the VI characteristics of a PN junction diode. So what you're supposed to do? So you should first explain the forward characteristics. You should explain the reverse characteristics. Then you should explain the VI characteristics of the diode with some values you need to mention. That is for the silicon, the knee voltage is 0.7 volts, and for the germanium, it is 0.3 voltage. So when the input voltage is slightly increases in the forward direction, the current will start flowing across the diode. When the input voltage is greater than the threshold voltage, then the current will start flowing. That is exponential increase in the current will takes place in the forward. Similarly, in the reverse bias condition, that since the diode will be in off state, so there will be a minimum amount of current will flows because of the minority charge carriers. If the input voltage is too much negative in the reverse bias condition, the breakdown of the diode will take place. Under that condition, a high amount of current will flows across that. So because of that, a high amount of reverse saturation current, you can see it in the diagram. So you need to explain like this by using these graphs. Okay. So the next one is, so you need to, sorry, I'm taking exactly time what I'm allotted. So 2 minutes I will be taking. Okay, so since I need to complete the syllabus, so that is why I'm taking some extra time. 1 minute just. So the first one is the barrier potential. So as I said, so what do you mean by barrier potential? It is defined as the minimum voltage under the forward bias condition at which the diode starts conducting. So it is called as a barrier voltage, or it is called as a threshold voltage, or it is also called as a cut-in voltage. The next one is forward voltage drop. So what do you mean by forward voltage drop? It is defined as the voltage drop across the diode when the diode is forward bias. The voltage drop across the means when you give an voltage to any one of the diode, some voltage will happen. So what is that voltage drop? That is nothing but a barrier potential will happen. Okay, so how much value? So for the silicon, it is 0.7 volts, and for the germanium, it will be 0.3 volts. The next one is forward resistance. So that is nothing but RB. So what you mean by forward resistance is it is defined as the resistance of the diode when the diode is forward bias. So means what? The resistance it has been exerted by the diode during the forward bias mode. So that we call it as a forward bias resistance. That is nothing but RB. For ideally for the conceptual wise, if I say that your RB should be 0, but practically it will not be 0, it will be having some few ohms. So we know that the resistance will be measured in terms of ohms. Okay, so this we call it as a forward resistance value. The next one is reverse saturation current. So when the diode undergoes breakdown condition, so the maximum amount of current which is flowing across the diode in the reverse mode, we call it as a reverse saturation current. And the next one is peak inversion voltage. So what do you mean by peak inversion voltage? It is defined as the reverse voltage at which the PN junction breakdown will happen and the diode starts conducting. So the maximum amount of reverse voltage what you are applying to a PN junction, so that we call it as a peak inverse voltage. Okay, so that we will be representing in terms of PIV rating of the diode. Okay, so we will stop it over here for the today's class. So the remaining thing we will take up in the next one. Okay, so thank you everyone for attending the classes. I will take the attendance from the report only. So thank you all.
Thank you, sir.
Thank you.
sir.
Thank you all.